So software as a service is awesome. What does software as a service run on? Well, what are the sort of demands on the infrastructure, right? If you're deploying software as a service, what does it have to be able to do? It has to be able to communicate. Users have to be able to get to the service somehow, so you need a network. You need to be able to accommodate widely varying amounts of users, and this is something that actually really just became practical in the mid-2000s. Until that time, sort of instantaneously scaling up was not something that a typical individual developer or small company was able to do, and now they can. And it needs to be up all the time. Once it's in the infrastructure, users expect that they'll be able to interact with it all the time. So, if you had software installed on your PC, you would expect that anytime you open your PC, you'll be able to use it. If you're relying on software that's in the cloud, you can reasonably expect that whenever you need to use that software, the cloud version is up and running. So, how do these demands get met? Essentially, in the 1990s, we started to move the internet infrastructure towards commodity clusters, which means instead of big mainframes, which actually until the mid-1990s were quite prevalent even for things like search engines, we're talking about mostly commodity PCs connected together with mostly commodity networking equipment. Now, I say mostly because software as a service and cloud computing has become so much the dominant mode of deploying software that a good amount of specialization has now occurred in how those commodity servers are built. But at the end of the day, from a programmer's point of view, they basically are souped up x86 or ARM PCs with souped up Ethernet. You program them the same way. The programming model is the same as truly commodity PCs like you would buy for personal use. And it was quickly realized that you can put a lot more of those together than the capacity of the very largest conventional mainframe server that you could buy. So if you run out of capacity on a mainframe, you need to forklift in another mainframe. If you run out of capacity in a cluster, you just need to add more nodes to the cluster. A lot cheaper than conventional servers because being commodity computers, they were already selling tens of millions of units into consumer markets. So all of the parts, the basic technology required to go into it, was already enjoying economies of scale. Whereas the non-commodity sort of mainframes that used to be the mainstays of data centers, far fewer of those are getting sold. So the price per unit of computation or storage was already going to be much cheaper if you could use commodity equipment. And in fact, and sometimes by up to a factor of 20 cheaper. What about dependability? We need these systems to be dependable. Well, a lot of redundancy. Buy more servers than you need with the assumption that once in a while some servers will fail or will temporarily have to reboot, and you just have enough servers to take up the slack. So it sounds really great on paper as a way to get dependability. And as a bonus, because the servers are all the same, they're all configured the same way, you probably have automated ways to update them, you don't need a lot of human beings to manage enormous numbers of servers. If you're careful about keeping them configured the same way, and you can use technology like virtual machines to do that, very, very few human beings, 2 or 3 human beings for tens of thousands of servers is actually not uncommon. And one of the highest costs of anything in computing and programming is the cost of human labor. So it seems like there's all these potentially great advantages. And indeed, those led to what Luis Barroso, who's one of the chief architects of Google, has called warehouse scale computing. Clusters very quickly went from being order of 1,000 computers to order of hundreds of thousands under a single roof. And that's because there was so much customer demand for the software as a service that was being deployed on those clusters. So what happens? At hundreds of thousands of computers per data center, you start getting really serious economies of scale. And in fact, Google and Amazon and others documented that they were seeing cost reductions of 3 to 8x in the sort of cost of computation and storage because they were buying these things in such huge quantities. You can get a volume discount from manufacturers. You don't need a lot of human operator oversight to manage very large numbers of machines. But the downside of all this was that those same companies found that only about 10 to 20% of the capacity of those data centers was utilized in steady state. So why would that be? Why just 10 to 20%? You build out 100,000 servers in your data center. You're Amazon. Christmas is coming. It's going to be a big shopping season. What happens after Christmas? Something happens after Christmas, kids. Anybody? Yes, New Year's does happen after Christmas. That is astute. However, where I was going with this, and I do have a point, The idea that you can have economy of scale by having huge numbers of servers and serve as many users as you want, it sounds great on paper when you have as many users as you want. But realistically, your demand is not going to be the same all the time. And Amazon was sort of the poster child for this, right? During the holiday season, their demand was order of magnitude more than it was the rest of the year. So it's like the parking lot in the mall, right? The parking lot in the mall has to be large enough for Christmas Eve. But the rest of the year, most of that parking lot is empty. So if you've got a data center and you're only using 10 to 20% of the capacity during your non-peak times, it might occur to you that you could sell off the capacity that you're not using. And to oversimplify only a little, that's kind of where Amazon Web Services came from. All of the facilities that Amazon Web Services has now, anybody use AWS, by the way? Has anybody tried it out? Okay, a number of people. All of that functionality that AWS rolled out in 2007 really was infrastructure that they had built internally to be able to meter and partition their own data centers so that they could manage it better. And the idea that you can now sell this by the hour to end users for a cost less than what most end users would have to pay if they bought equipment themselves, what an interesting idea. And that really only happened in 2007 when Amazon first launched EC2, the Elastic Compute Cloud. And the idea was very appealing. You could buy server capacity by the hour. They started out at about 10 cents an hour. Now you can get it for 2 cents an hour. They even have a free tier where you can get it for 0 cents an hour. But the really, really cool thing that no one had ever done before was this, that you could rent 1,000 computers for an hour, or you could rent a single one for 1,000 hours, and it was the same amount of money. Never before had there been an opportunity where any one of us, by plunking down a credit card, could say, I need 1,000 computers because I have a 1,000-way parallel job that I could run in about an hour. That was huge. And that's what we now call public cloud computing or utility computing, take your pick. It basically means anybody at all can rent capacity for the amount of time and number of machines they need. There's now 3 or 4 different providers that are competing in this field. And by the way, because those data centers are managed by people whose sole job it is to do that, they will probably do a better job than you if you owned those computers and had to hire your own technical personnel to do that. So another way of saying that is that the total cost of ownership from the point of view of the app developer, that's us, is actually more favorable. Because we're not just getting the computing resources, we're essentially getting the human beings who are managing those resources on our behalf, probably more thoroughly than we could. We can scale up and down instantly. So if you decide that all of a sudden, instead of 1,000, you need 2,000, in the old days, you'd have to order 1,000 computers, and it takes weeks to get them and rack them and set them up. With AWS, you just say, I want more. And as long as your credit card doesn't get declined, you can expand elastically, basically, as far as you want. And that was really important because that's the thing that leveled the field for people like us. As an individual developer, you could now aspire to have an application that was so popular that it could scale from nothing to millions of users in weeks, and there was actually a way that you'd be able to handle, to serve all those millions of users. That had never been a thing before, and probably one of the earliest success stories about that was a game called Farmville. If anybody remembers Zynga's Farmville, they got to 1 million users in their first 4 days. Within 9 months, they had 75 million users. Prior to that, the largest, most successful online game had been around 5 million users, and they did it all on AWS. Imagine if you were Zynga, and you went to some investor saying, we have this great idea for a game. We think we're going to get 75 million users in 9 months. We would like enough money to buy thousands of computers. Right? That's a hard argument to make. But if you're only buying computers as you need them, and then when people get disenchanted of your game and they move on to Candy Crush Saga, you can just release those computers and not pay for them anymore, that's a very different value proposition. So today we sort of take it for granted, but in 2007, this was huge. Those of you who don't know this, Netflix basically does not own any of the infrastructure that they use for streaming movies. They are perhaps the single largest customer on AWS. And there's great talks that you can look for online where they talk about why this has turned out to be such a great decision. So even at the scale of something like Netflix, this has really refactored the way that we think about buying computation. Right? So again, today, this is something we seem to kind of take for granted. But as early as, or as recently as 10 years ago, this is not the way things were done. This has all sort of happened within your pre-college lifetimes. Question? Yeah.
Isn't it kind of dangerous to be dependent to another company for something so big? Like if something that happens to Amazon, like web services, that means that like Zynga, Netflix, most of the other companies would go down too, right?
That is a great question. So the question is, isn't it kind of a big risk to sort of put all your eggs in one basket? Because now all these different companies using AWS, if AWS goes down, all those companies basically go offline. And there have been some very visible outages in the past where AWS has had a failure that significantly affected one or more of their clients. However, one of the ways to mitigate that is AWS has multiple data centers, not only in the US, but outside the US as well. And any company that really needs that level of redundancy can set up operations in multiple data centers and fail over. Now, the engineering to do that is somewhat beyond the scope of this course, but the real lesson is, even if you weren't using AWS, even if you had all of your own equipment, you would still have to worry about that, right? If you have all of your equipment housed in, Chicago in a data center, and Chicago gets hit by a snowstorm and the power goes out, you still have the same problem. You would have had to make plans to have redundant infrastructure in other physical locations and have the software mechanism to fail over if something happens to go wrong. So Amazon is now providing the infrastructure to do that and a level of professional management to do it. You still have to do the software engineering to get it right, but I think there's a strong case to be made that the management of the technology is still in better hands with people who are only doing that. And certainly, I feel like my data is probably safer at Amazon than on any machine that I own, which in fact is why that's where it lives. By the way, I don't work for Amazon or anything like that. I get no kickback. But this is one of the reasons that this computer is like 5 years old. I wish I had a bumper sticker or something that says my other computer is AWS. Because really, this is what I use for personal development, but anything else that's reasonable, that people care about, I deploy in the cloud, and that's my backup. Other question? Yes?
So if you're using server computers for computation, it makes sense that we could scale up and down by letting other computers do this task or that task. But in clients like Netflix, where they have to store data, how does that work? Does Amazon store a lot of data to a lot of computers and delete it away when they don't use it, or how does data storage work across a big warehouse?
How does data storage work at warehouse scale? It's not a 1-minute answer, but I'll give you a sketch of the answer. It is not, in a setup like what Netflix would have, it is not necessarily the case that any computer in any data center that is under Netflix's management is always able to serve a copy of any video stream. So for example, some movies are super, super popular. The ability to serve those movies is widely distributed because they expect a lot of different people might want to watch them at the same time. The capacity for serving much less popular stuff, you might be directed to one of a small number of servers that has that copy of Mrs. Miniver or some other classic 1945 film that very few people know about, but they have to have it available for you. So there's a fair amount of allocation that has to go on, and the general answer is not every computer can always do every task. And there is a risk that if Mrs. Miniver suddenly becomes super, super popular, they won't have enough servers available to provision it, and you'll get that message that says, we can't stream this right now, but try again later. And then they can start doing background copies to move more copies of that data closer to where it's needed. So I'm oversimplifying a lot, but that's the idea of how it would be done. Okay? So we love the cloud. We love software as a service. We're going to use it. It all sounds great on paper. Inexpensive warehouse-sized clusters. They cost roughly nothing per hour. The potential for unlimited scalability. But you have to design scalability into the software too. So a lot of times, I've had students who will come to my office hours and say, hey, I'm working on an extracurricular project. It's going to be a software as a service app. It's going to be awesomely popular. We want it to be highly scalable. That term masks a tremendous amount of complexity. So one of the things that we are going to discuss during this course, hey, maybe you will be the next Farmville or Candy Crush or whatever, but thinking about, as an app developer, how to avoid painting yourself into a scalability corner. Because scalability isn't magic. There's a lot of great things about the classic architecture of software as a service that we're going to be using that make it somewhat easier to realize the potential for the scalability that you can get from cloud computing, but it's not free. And it is absolutely possible to do things that will shoot yourself in the foot. And it's not because Rails doesn't scale. It's not because Node.js gives you the power to get close to the metal. It's none of that stuff. It is thinking about architecture and what operations you're asking your app to do that fundamentally have scaling problems. And this question that we had before about, well, what if your app is serving data and not every user wants the same data? How do you know that you've got copies of the right data near the right user? That's an example of a scalability issue, right? So there is no magic bullet in terms of language, technology, stack, or anything like that that will make your app more scalable. But when we come to a juncture where we say, you know, if you're not careful about how you use this functionality, here's the reason why it could become a scaling bottleneck for your app, those are things that we are going to highlight. And one reason that I think you'll find that very useful is, even though we're going to be deploying our apps on Heroku, which is a pretty standard infrastructure or platform as a service, they provide a lot of managed stacks for you. And I've been asked, by some students, well, isn't that really limiting in terms of if you want to scale out a lot further? The reason that we focus on it in this class is because the exact same pitfalls that could come to bite you in the butt on Heroku and thwart scalability there, even if you had a different do-it-yourself, I'm writing all my own code on my own clusters, you would still have to work with those exact same issues. So the kind of thinking we need to get you into is exactly the same for both cases. Things that thwart scalability will bite you whether you're using somebody else's curated stack or whether you're trying to do it yourself.